Okay. Well, we can generalize this pretty easily now. We see that if our large cube is x centimeters, now there's a caveat here. X would have to be a multiple of 10 in order to really apply this reasoning in all its detail, but we can kind of extend that reasoning. We'll talk about that a little bit. Okay, in general then, if the large cube is x centimeters, I didn't write it down where x is a multiple of 10, so that we can divide x by 10 and get an even, or get a whole number. Then I say it's going to take x over 10 cubed, 10 centimeter cubes, to make an x centimeter cube. Okay, and if x is 4,000, as it is here, isn't this exactly what we've done? Okay, we let x be 4,000, divide 4,000 by 10, and cube it. That's where we get our 64 million. So if we just use this as kind of a formula, we don't want to do that, but we want to understand that this expresses what we've been doing. If we put the number of centimeters from this, or this, or this problem into this form, then we get the number of 10 centimeter cubes it takes to make a cube of that size. Now, a bit of terminology. X over 10 is the ratio of the length of the sides. So, if we have a 40 centimeter cube, the ratio of 40 centimeters to 10 centimeters is the ratio of the sides of our 40 centimeter cube to the sides of our 10 centimeter cube. And if we cube that ratio, that gives us the ratio of the numbers of cubes, okay? And that would actually also be the ratio of the numbers of small cubes. I'm not going to talk too much about why that is. We'll extend this next time, but these ratios are very important. Okay, and just to make sense of this statement here, if x over 10 cubed is 64, as is the case with a 40 centimeter cube, then 64 is the ratio of how many small cubes we need in a 40 centimeter cube, which is 64,000, to the number in our 10 centimeter cube, which is 1,000. Okay. It's also the ratio of the number of 10 centimeter cubes, which is just 64, and many other, well, this is part of something quite general that we'll be developing, okay? So just kind of think in terms of these ratios, and the idea then is that if this is a ratio of the lengths, then the length of the volumes of the cube, the lengths, the ratio of how much is inside the cubes, appears to be the cube of the length ratio. And there's very good reason why that is the case. And that actually extends to any two geometrically similar solids. The ratio of the volumes is the cube of the ratio of some dimension.